how to approach it. All right, so approximate the 0 of that function. So you have this function f of x, and it is e to the negative x minus it. So you have that. Sometimes it's phrased like this. Sometimes it's phrased other ways. The question could have said, I don't know what the next one says. It might say this: find the intersection. It's another way they phrase these. Find the intersection of x and e to the negative x. These two say the exact same thing, right? And you want to realize that for these kinds of problems. Why do they say the same thing? Because what does it mean to find an intersection of x and e to the negative x? That means you set them equal to each other, correct? Yeah. But since Newton's method is a root-finding method, it finds zeros of functions. You subtract this to the other side, and now you have a function equal to 0. So then you declare your function to be the x minus e to the negative x function. And it's now the same problem they just handed you on the screen. See what I'm saying? So finding intersections of curves can always be translated into a root-finding Newton's method problem. That's the other basic way they introduce these problems. Okay? All right. They give it straight to you. They said find a 0 of this thing. Find if this thing equals 0 by using Newton's method. Continue the process until 2 successive approximations differ by less than 0.001. So we need the successive approximations to agree to 3 decimal places, basically. Okay? All right. So
you said the x minus e to the negative x. That's the
function we're starting with.
Okay.
They're saying find where it equals 0. It says d0, so there's only 1. All right. So we need to construct the formula. So x next equals the previous x minus, I need to put the original function above, x minus, we'll just compute it first. The original function above, x minus e to the negative x, over the derivative, which is 1 plus e to the x. Is that right? Is that right? Negative x? Okay. So there's our expression. So x previous minus e to the negative x over 1 x previous.
Why is it 1 plus e?
Yeah. That's the derivative. 1, and you do the chain rule on this, the negative comes down.
Okay.
1 plus e to the negative x previous. So there's our formula. Again, you're going to put this in your calculator. So you could take this expression and go ahead and multiply it over here to this one, and then add them together. I don't know that's such an advantage in this case, though. I'm just looking at it. Yeah, I don't know that matters that much. I don't think it's going to be that helpful. So then you would take your calculator and put that function in. Does this thing have a calculator? It's supposed to. You used it before, right? It probably didn't work. It broke down. Is this where it broke down? Or did it work? Have you used this before?
I don't know. No, you haven't used it.
Have you seen me use a TI Smart View?
No.
Sure.
Maybe the past, like.
Right. Unavailable. Yeah, it won't work again, right? Yeah, I tried to use it.
Go to like working and .com.
This thing what I should do. All right. So anyway. So first thing you need to do is pick a value which is perhaps close to an actual root. It doesn't be that close. So pick a number. What do you think?
1.
1? Okay. So if we pick x naught to be 1, then when you plug it in, you will get that x1, the next x, is 1 minus e to the negative first over 1 plus e to the negative first. You compute that. Whatever you get for that, that is your x2, right? I'm sorry, that's your x1. So then it's going to be your x1, and you're going to plug that in to get your x2. Plug that into the expression, and just keep moving. That's all you do. Keep moving until you get 3 decimal places that agree. That's all it is. It's not a complicated scheme, really. You guys handle Newton's method? Baker, Newton's method make any sense? Yeah. The other thing you can do to start the process in an efficient manner is to actually treat this, like I said over here, treat it as an intersection of two curves. So you could plug this function into your calculator and see where it hits 0. You could do that. Or you could plug these two functions in your calculator and see where they intersect. Right? Where that's happening, that's the x you actually want. So start at something which is close to that. So the Newton's method doesn't take too many rounds to get through. Right? It'll converge faster. What's the next one? Okay, this one's like the example I did. It's just like what I did.
The method also works when the slope is negative.
Yeah.
That should be plus, no, the same minus. The x n minus 1.
This expression here?
The x n equal x n.
Oh, this one up here?
So if the slope is minus, also works, so this should be plus.
Are you saying because it'll make this positive?
It's also the same.
Yeah. The problem is, if you really want to know something, the problem is the devil's in the details, like everything else. So if you have a function, let's say a sine function, it's a classic example. So let's say you want to approximate this root, and then you start down here by accident. You start here, right? So you're here, and you take right.
If you start from the left.
Okay, start anywhere you want. So I start here, okay?
Yeah.
Start here. So if I start there, then it's going to shoot me down over here, right? Down here. How? Right? So now I'm looking at this value, and that puts me here on the curve, and that puts me here on that. But that's going to intersect over here. It's actually putting me further away. So on badly behaving curves, Newton's method's first selection is extremely important. Does that make sense what I'm saying? Is the picture kind of ugly? Let me draw it again. I'll make the same, make a sine curve. A sine curve. So you want to approximate, whatever, we say this one? You want to approximate that root. So if you start here, it maps you up to here, and when you take the slope of that, it puts you over here somewhere. And then that maps down to here, and that slope is like this, and that puts you up on the curve over here, right? And it intersects the curve here. It doesn't intersect anything down here. There's no more curve down there. So where does it intersect? Over here. And then this puts you where? Oh shoot, there's no curve over here. I'm getting further away. That's going to shoot me down over here, right? Because it's going to curve back up here, and it's going to intersect there, right? And so forth and so forth. So sometimes Newton's method does not converge, right? Because of the initial choice. If you would pick something further down this curve, though, then if you pick something here, okay, start up here, maps here, then it maps down very close, over there, here, and then up, and then it's almost on already. So just depending on where you start can make a huge difference in a badly behaving curve.